this morning. Let me quickly make some room on the whiteboard. So, I don't know if there are any questions that any of you would like to pose right away. We were in the middle, last Friday we were in the middle of my illustration of well, derivation of what we will call the Navier-Stokes equation. Navier equation or Navier-Stokes equation. And I think I spent quite some time to explain this relationship. Okay, so a few things to keep in mind when you look at an equation like this. We are dealing with vectors, okay? So these are really, since we live in three-dimensional space, these are really three equations, one per component of the vectors that are involved. F being force per unit volume. T is force per unit surface. These are the surface forces. And U is a displacement, which I differentiate twice with respect to time so that I get acceleration. Rho is density, is mass per unit volume. V is the volume that that we are considering, which can be any volume. This law has to hold anyways. It can be any portion of a medium. Del V is the boundary of this volume. Importantly, this is not the boundary of the medium, okay? This is not the outer surface of the Earth. It could be, but it doesn't need to be. Because this equation is basically Newton's law, has to hold for any portion of any medium that you might consider. So then what I did was I started to introduce basically one of the most important concepts in not only in seismology, but in general in geophysics, that is to say the concept of stress that probably you've met before, but in any case, we'll spend a few minutes to review it together. Okay.
Sorry, sir.
Yes.
Can you see on chart?
I couldn't hear you. Say that again.
Can you see on chart?
Oh.
I mean the second integration divide as just no. Integration. Yeah, yes.
No.
Div s.
What this means, this is del V. So if this is the volume that I'm considering, what I call del V is the outer surface of that volume, okay? It's a boundary, the border, whatever you call it, of V. You can call it S if you don't like it, but you have to accept that S is not just any surface. It's the surface that bounds V. Okay. Does that make sense? Okay. Thanks. Yeah, that's important. Of course, we have to be careful about these things. All right.
Thank you, sir.
Sure. Good. So, great. So now let's talk about these surface forces a bit more. I explained to you last time that since our volume is arbitrary, let's just take it to be a cube, more approximately a cube. And so by doing that, remember, I was able to define 9 parameters, 9 variables, 9 values that are enough to fully describe the surface forces that act on this box. Okay, and these are the components of each of these forces on the faces of the cube. So, for example, if I call the axis, let's call them today, let's use a slightly different notation, which I think is better, and we shall call them x1, x2, and x3, okay? So if this is x3, I can call, it makes sense to call this would be the face number 3, and so I can call T31, T32, and T33 the 3 component on the surface force that acts on the face number 3, and so on and so forth. Or even better, actually, I will call, since x3 is growing in that direction, I will call the forces that act on this surface T31, T32, T33, and here I have T31 plus delta T31, and so on and so forth. Likewise, here I would have T21 plus delta T21, and here you have T21, T22, T23, and so on and so forth. So the consequence of the point of this is that if you want to know the surface forces around this point, you need a vector, a tensor, sorry, that has 2 dimensions. And I'm going to call it tau. Okay, I'm going to use a Greek letter tau. And I'm going, and that's how I like to do things. I'm going to underline it twice to remind myself that this is a second order tensor. It's a matrix, it's got 2 dimensions, okay? If I underline once, it's only got 1 dimension, it's a vector. If I underline twice, it's a tensor. And it's going to have components, tau 1, 1, tau 1, 2, tau 1, 3, tau 2, 1, tau 2, 2, tau 2, 3, tau 3, 1, tau, etc. etc. Okay. Now here I'm skipping a little bit of material. But what I'm just gonna tell you that basically, if you want to know, for example, the force T that acts on surface number 3, you multiply tau scalar by a unit vector n that is a unit vector, so it's got magnitude 1 and points in the direction of the axis x3. Okay, so I don't know. I make sure, like, I would like you to be careful with the difference between this capital T here and tau. Okay, capital T, it's not, I don't know how useful that is for you to understand what I'm talking about. Basically, capital T makes sense only in this Cartesian geometry. But what I'm trying to show you without doing all the rigorous math is that if you know 9 number here, if you know the components for each surface, you know the 3 components of the surface force, then you know everything you need to know about the surface force. Now this tau, it's a slightly different entity. Okay, it's more general, because if you know tau, then you know the stress independent of the orientation of the surface. Okay, so T1 is for surface number 1, this one, okay, that points towards me. T2 is for surface number 2 that points that way, and T3 is for the upper or lower face. Okay, it's for the surface number 3. But I could, well, it gets complicated, but in principle, one could prove that it's enough, okay, to define a vector tau like that, such that if you dot multiply, meaning it's a scalar product between a vector, a tensor, and a vector, with the unit vector that points in the right direction, you get the actual surface force. So here you have a force per unit surface, which is a vector. And this guy is what we call the stress tensor. Okay. So the stress tensor carries all the information you need to quantify, to calculate the stress on any surface, no matter how it is oriented within your medium. Okay, so on the diagonal of the stress tensor, you have tau 1, tau 2, 2, tau 3, 3. So that corresponds to what here I call the capital T 2, 2, 3, 3, 1, 1. So those are the those correspond to the actual pressure. Okay, the first perimeter surface that is perpendicular to the surface itself. The rest is shearing. The rest describes the shear. Okay. So also make sure that you understand what I mean by dot product between a vector and a tensor. It means basically, if you don't remember it, you know, it's a product, like it will look like that. And here you have, like for example, if we take n3 will be 0, 0, 1, because it's a vector that points in the x3 direction, and so this would actually give me the first line by the first by the only column here. It gives me tau 1, 3, tau 2, 3, and tau 3, 3. So in that case, that corresponds indeed, well, with this guy. But the stress tensor, again, you can use it no matter how the surface is oriented. So it will work even if the surface, even if the unit vector here didn't point in the direction of one of the axes, but it could point in any possible direction. So yeah, so basically you can, once you accept that, you can extend this concept to a volume of any possible shape. You kind of have to accept it. I will give you some books if you want, if you want to strengthen your continuum mechanics, or if you want to learn it because you haven't learned it before. I'm just touching briefly on this because I have to move on to waves. That's the purpose of this course. But if you take a geophysics or geodynamics, a solid earth geophysics, geodynamics course, you'll meet these things again, and maybe you met them before and you've received a much better explanation. But what I want to do, the reason I'm doing this, all I want to do really, I want to show you a little bit, at least give you a feeling of how the Navier-Stokes is derived. So the point here is that I can replace T here with tau dotted with n. Okay, and n here is a unit vector that's everywhere perpendicular to S. Okay, so if this is your volume, and this is its outer surface S, and the vector n changes along S in such a way that it's always perpendicular to S, and its magnitude is always 1. Okay, and any questions? Let's move on to more exciting stuff, but let me do a little bit more math, because to finish the derivation and get Navier-Stokes, which is a really important equation in not only in geophysics, but in all continuum mechanics, we're very close to it. All we need to do is apply a theorem that's called Divergence Theorem. And I want to show you how that works, because we have, from the lectures I gave you so far, we have all the tools we need to understand that theory. I'm not going to give you a rigorous proof, but I will try to convince you of why the theorem works through an example. So the divergence theorem is useful when you are in a situation like this, where you have an equation where you have both integrals over volumes and integral over surface. And in this particular case, also, the volume over which we are integrating is arbitrary, okay? The only constraint being that it can be very small. Because ultimately what we want is not an integral, we want a differential equation that holds in every point of the medium. So to get that equation, basically, as you will see in a minute, we want really to get rid of the integral and just have an integrand, the argument, if you want, of the integral that we will equate to 0. But you see that in detail in a minute. To get there, basically, one way to do that would be to turn the surface integral to an integral within the whole volume. Remember that S is the frontier, the border, the boundary of V, okay? So now think about this. Think, for example, of, again, you have this volume V, and the material that's inside, grazie, that's inside V moves around. And so it's got some displacement that I call U. Okay, so there's a displacement field inside V. Maybe it's some sort of expansion. Okay, maybe this is a gas, could be a gas or anything. It could be a viscous medium that's heated and it expands, for example. Okay, so it expands. So the volume changes, and if you remember, I've shown you the other day that a change in volume can be written, if you know the displacement, and I'm going to call it delta U with the delta to remind myself that we are talking about small displacement. Actually, no, that's not even true. I mean, we're not talking about necessarily small displacement, but remember, it's a change in the displacement across each cell. So that gave me, the other day, it gave us this relationship. Now let's stay with the new notation where we use numbers to denote the three axes. Instead of XYZ, we use 1, 2, 3, X1, X2, X3. So delta U2 is the change in displacement along the X2 direction, and I have to multiply it by the surface that's perpendicular to that, and so on, and so forth. And from that, if I divide both sides by the volume, which would be delta X1, delta X2, delta X3, I get the divergence of the displacement. Okay, here, this is the nabla, but here I have a dot product, so that's a divergence. And that's a way to that's a way to understand what divergence is, right? And maybe it makes more sense to use a capital delta here, because otherwise I have too many small delta. So the change in volume caused, okay, the change in volume due to this displacement U coincide, the relative change in volume coincides with the divergence of the displacement. A divergence-free displacement results in no net change in volume. Okay, so now let's consider what does that mean. What does that mean in terms of mass? Okay, this is matter within this volume that also has a mass. So, or rather, I should say density. Mass is conserved, but that density will change if we have an expansion. So, density is mass. I call it rho. Is mass over volume. And so, yeah, if I differentiate rho with respect to volume, I get minus m over v squared, which means that basically delta rho is approximately equal to minus m over v 0 well, doesn't matter, m over v delta v over v, which is nothing but minus rho delta v over v. So you can also write that delta rho over rho is approximately the same as minus delta v over v. Not surprisingly, okay? If the volume grows and you have the same amount of mass, which you must have because the mass is concerned, then the density has to decrease. Okay, so a positive change in volume results in a negative change in density. And since density is inversely proportional to volume, the relative change is the same. It's a linear sort of relationship. Okay, so that means that basically that the divergence is also, it's also proportional, it's also the same as a relative change in density, except that the sign has to be switched. Okay, so now I show you something interesting, I hope. It's, yeah. If you, on the other hand, now think of a finite volume, okay? So remember that rho I mean a constant volume, okay? And remember that rho equals m over v. So for the exact same reason, you can show that now instead of differentiating here, like if you take v to be constant, you can prove that and it sort of works in the same way that yeah, also delta m over m is just the proportional to the divergence of u. And of course with a minus sign. No, with a, wait a second, no, with a plus sign, because if v is constant and the density goes up, yeah. If this is a bit strange. Yeah, should be good. Okay. So, so the point here is that the divergence of u equals no, excuse me, delta m equals minus m divergence of u. So let's apply this now to a small let's apply it first to a small element of mass, that coincides with rho dV, okay, for a small volume dV. Yeah, I don't need this anymore. So then the total change in mass, it coincides with the sum of rho, or the integral over the whole volume in question, times dV. And
Excuse me.
and basically what we have, yeah.
I don't understand how delta m over m equal to delta u.
See it again.
And the last line, delta m over m equal to the del of u. So I don't get that part.
Yeah, it's a divergence. Yeah. Well, that was the well, yeah. I think I didn't use the best notation possible. So let me try to do that again. So we obtain that delta V over V equals the divergence of U. This we've seen before, so it should be okay. Then you can play some games now, because if you multiply, basically, if you just multiply this guy by density above and below, and I guess I got a wrong sign a minute ago, sorry. This is a change in mass, and this is the total mass, right? So, and also, sorry, I'm kind of switching around between small delta and big delta. That's not very helpful. I'm sorry about that. But this should be good now. Okay, so correct your notes. This is a much more straightforward way to derive this. So this is the first thing that we discovered. This is the second. And then I've also shown you that minus the divergence is equal to a relative change in density. Of course, yeah. Yeah. If you take this equation, okay, you can also write that the change in mass is equal to the mass multiplied by the divergence of U. You just multiply both sides by the initial mass. And if you apply this to a very small mass, rho times a small volume V, you obtain that Well, that's still true. So you have to have this result. Now, if I integrate and then over a larger volume, okay, that includes all these elements delta V, I will get a total change in mass associated with this larger volume that's equal. Let's assume that rho initially is constant, so rho integral delta U times del V over the whole volume. Okay, think about it for a minute. I also want to check one thing in my note that is perturbing me. Okay, now let's think about another way to write this change in mass, right? What is this change in mass? Basically, it's remember how we wrote a change in volume in our box, in our simple box configuration was the divergence of U. That's the relative change in volume. Excuse me. We also wrote it as we remember that when we calculated that, we have this is here we call the delta x2, this length here, this we call delta x1, and that would be delta x3. So for example, the change in volume right here due to this particular expansion would be U, the displacement of particles near the surface, so U2 in this case times delta U1, sorry, if we call this x1, this x2, and this x3, U1 times delta x2 delta x3. So if, for example, okay, consider that this is nothing but U, whatever the displacement is around here, multiply dot product by 1, 0, 0, so that we get U1 times del S, which is, well, which is nothing in this case, times, but delta x2, delta x3. So now if I integrate, so I can also write this as u times n times ds. Okay, ds being this particular surface. And if I integrate this, integrate of u times n ds over the entire surface that bounds my element of material here, and if I multiply it with rho, the density, I also get the total change in mass. You know, how much mass has gotten out of my initial volume, V. Okay, if now I keep V constant and I calculate how much mass has left V, because it's been displaced across the surface that bounds V, well, it's just the integral of this change in volume, right? So here we go. So these two quantities must be the same, which boils down, if I cancel rho out, it boils down to integral over the whole volume of the divergence of u equals the integral over the surface that bounds V of u dotted with n ds. Okay, and that is the divergence. What I gave you is not a rigorous proof, I would say. I try to use the idea of conservation of mass to show you that it makes sense. If you, I hope I've shown you that you can write, if you consider a constant volume, okay, and material is flowing in and out of this volume through a displacement u, with the math I've done, I hope to have convinced you that the change in mass of that fixed volume can be calculated through this formula. Okay, density multiplied by the integral of the divergence of u over the whole volume. Because we've seen together that the divergence of u is proportional to the relative change in mass. I hope to also have shown you that the change in mass can be written as an integral along the surface of the element of material of the displacement multiplied by the normal to that surface. So two ways to write the same thing. We can equate the results, and this is what we get. And this holds, the reasoning in fact holds, even if we are not dealing with mass or volume, density, and so on, but whatever this vector u is actually. And so we can certainly apply this idea to this equation here, because notice we are lucky actually here we have a tensor, not a vector, but a tensor. It's just a 3D in 3D. A tensor is just a combination of three vectors. So for each column of the tensor, we can apply the divergence theorem and simplify. Well, and reduce the surface integral to a volume integral. Okay? So the trick is to here, basically what we need to do is we need to take the divergence. Okay, so I apply exactly this equation, and this becomes the integral over V of the divergence of tau integrated over volume. All right. So let's write it down properly, and actually let's write it as a useful exercise, and also because it's going to make our life easier in a couple of minutes. Let's write it component by component. Okay, so here you have, I've chosen to use the vector notation. So I underline things once or twice to remind myself whether they are vectors or tensors, and I have to be careful with remembering what I mean if I use a dot product rather than vector product, a cross product or whatever. So here I have a dot product, and I have to remember to know what that is. Let's write it component by component. So I have, these actually represent three equations, one by components. I use the symbol lowercase I to denote, to distinguish the components from one another. And for each component, I can write the following. I can write the integral over V of the ith component of F of the volume force plus, again, the integral over V, and this is tricky, okay? The derivative with respect to J of the ij component of tau. That's what you do when you do the divergence of a tensor. I could also write JE here. It doesn't matter because I don't have time to prove it in this course, but you can show based on how we defined it that the stress tensor is always symmetric, okay? So JIIJ doesn't matter. And also, this is a divergence, okay? So I have to apply the formula of the divergence. Remember, the divergence of a vector is the sum of the derivative of each component with respect to the corresponding distance, to the corresponding Cartesian coordinate. So del U1 over del X1 plus 2 plus 3. This is just a definition of divergence. So here, basically, I am implicitly summing over the index J. I'm using what people call Einstein's notation, where if an index is repeated in an expression, it automatically means that you are summing over the index. So del tau Ji over xj, which is the same as writing delta tau ij over xj, because tau is a symmetric tensor, is exactly the same as writing sigma sum over j from 1 to 3 of the same thing. So this is just a matter of notation, okay? And minus integral of rho del square ui over del t squared, volume integral again. And then I brought that to the left-hand side, and everything summed together must be 0. Or it doesn't matter. Let's keep it at the let's leave it at the right-hand side. It doesn't matter. So, okay, so now this is an important step forward, because now we have, well, we are integrating everything over volume, right? So, yeah, actually, let's bring it, sorry. I prefer, yeah, let's bring it to the left-hand side. So you see more clearly that I can just pull everything within just one integral sign. So fi plus, yeah, here I also have dv, plus the divergence of tau minus rho, the acceleration, integrated over dv, and then equals to 0. But remember a very important point: v is arbitrary, okay? Ultimately, we never said like that v has to fulfill some important property. V is just an arbitrary volume that we take anywhere within our medium to study its general properties. We could, it's a sample that we could take everywhere within the medium. And also its outer boundary does not correspond with the outer boundary of the medium. So it's really just, think of it as a sample, a place where we deploy our instrument to study how the material in general behaves. So, and it can be, and it needs to be small, and it can be as small as we want. Ultimately, we want to converge it to nothing, to just a material point. So this implies that we can basically think of an arbitrary small volume so that we can basically get rid of the integral. You know. If the v goes to 0, ultimately the requirement the integral is 0 is the same as the requirement that the integrand is 0. And so we get Navier-Stokes equation, which reads like this. And I'm going to write it both in vector and component by component notation. So in continuum mechanics, that's basically the counterpart, the equivalent of Newton's force equals mass times acceleration. It's like Newton's law written for one point, for each individual point of a large, arbitrary large or small or whatever medium. It's got to hold at every time and at any point of our medium. And yeah. Any questions about that? I have a bunch of things that I want to tell you about this.
Sir, I don't understand why you consider that the volume we have to admit that the volume is enough small that we can the derivation can goes to 0.
So I guess the way I would, if it was me, the way I would think about it is like in general, you have an integral of a function over a volume, okay? And the volume is arbitrary, and if you accept that, I understand that you accept the idea that we can take this as small as we want, right? So let's say that f depends on x, y, z, and maybe if this is like x and this is f, and I'm not drawing. Well, I don't need to draw this, but basically, now imagine that you look at this function f, and this function changes as a function of x, y, z. But once you see it, you have this function in front of you, you can say, okay, I'm going to take this volume so small, I'm going to keep making it smaller, smaller, smaller until within that volume, f doesn't change anymore. And I can always do that because there's no limit to how small I can take that. Okay, so if this is so small that f becomes constant within it, this is approximated by f x, y, z at near the point that basically identifies the area where I'm looking at, multiplied by some extremely small but finite delta v. Okay, so if this is required to be 0, the delta v even simplifies out, and I'm left with the integrand equals to 0. Does it make sense?
Okay, yeah, thank you, sir.
Yeah, these are all questions that I asked myself to myself at some point in studying and learning and learning to teach all these things. So it's there are a lot of very subtle points like these, and it's good that you are picking that up. Now, this equation has not solved our problem yet, because ultimately what we want to be able to make some predictions about how our system is going to evolve. It's going to respond to some force, like we did for the string, for the gas. Ultimately, you want a differential equation with just one unknown function, which ideally would be displacement. So typically, this is either weight or a source or nothing. If we neglect gravity, which in seismology, it's okay to a large extent to do, then the body force, there are no other distance forces acting on our system other than gravity. So basically, this F could cancel out, unless we want to use that to represent an earthquake, for example. Okay, that is one way to describe an earthquake of an explosion, the source of the displacement that you are going to observe. And in some textbooks, in some articles, you'll find that. I prefer actually to use the same approach that we used in the case of the string, where we solve the problem prescribing some initial conditions. So then, if we do that, basically we can totally get rid of this guy. The two approaches, prescribing a force in this equation versus prescribing an initial conditions, are actually theoretically related. So if you find a solution to the initial condition problem, you can also find a solution. You can basically use it. It's related formally, and the relationship is known to the solution to the forced problem, okay? And if you're curious about these things, the keyword is Duhamel principle. It's the relationship between the solution to the initial condition problem and the solution to the forced problem. But I'm telling you that just as a curiosity, okay? For the level of this course, I wouldn't require you to learn the Duhamel's principle. I'm just telling you, like, if one day you go back to your notes because you need to use this stuff for some more complex application, this might be useful. But for now, you don't need to remember Duhamel's principle. So basically, anyway, this is either something that we prescribe, okay? Like we say that at time t, there's an earthquake that can be represented by a force F, such and such, blah, 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 applied over the surface of a fault, blah, 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 blah. So we could prescribe that, or it could be gravity. If it's gravity, the mass gets very complicated, but basically this becomes some sort of function of the displacement. The displacement of the mass gives rise to a change in the gravitational force that's applied to that mass, and you can mathematize that. And here you would have some complicated function of displacement. It's annoying, but it's within the realm of things that we can solve. Because then, you see where I'm going, right? We want to have a differential equation with the displacement as the only unknown. So one way or the other, you know, this part is solved. It's either a function of displacement that we can find out analytically, or it's something prescribed. Okay. Now we are left with the problem of writing Tij, tau ij, in terms of displacement. And that's a pretty complex problem. But
Sir,
yes,
here tau is a stress.
yes,
Yeah, it's a tensor of stress.
yeah. Tau
So
is
this,
stress tensor.
so here the differential equation here we have the relation between stress and displacement.
Yes.
U. Okay, okay, thank you.
The differential equation, so here's a differential equation by definition. You have functions and there are unknown functions with their derivatives. But it's a differential equation with two unknowns. One is a displacement, and the other is stress. What I was trying to say, I was probably not completely clear.
So
Yeah.
here we have here if we can solve this equation differential equation, we can obtain the relation between the stress and its consequence on the displacement.
Well, yeah, but you can't really solve it because you don't know the displacement and you don't know the stress. So you have two unknowns and only one equation.
Yeah.
That's what I'm trying to say. The other thing that I was trying to say is that this guy here, F, which I'm neglecting, but if I didn't want to neglect it, in any case, if that would be associated with gravity, and I could write it in terms of displacement. It's a bit tricky, but you understand the physics, right? You change the position of the mass and the gravitational force changes, and so F changes. So that was the first thing that I hope is clear, but we decided to neglect gravity, and so this term is gone. So now we are left with this equation, and you're perfectly right that the differential equation relating stress and displacement, but
Tarek, mute your mic.
Okay, thank you. Sorry.
Okay.
it's okay. Yeah, so what I'm trying to get to is that we can solve this issue here because we also have Hooke's law, which is an experimental law relating stress and displacement. So but I need actually, I'm going too fast. See, if we know what kind of medium we are dealing with, if we study how this medium responds experimentally, it responds to pressure, to shearing, we can establish some empirical relation between these two entities. And before we move on with this, it's important that you realize that different media and also in different experimental setups will behave, will respond differently. We respond to the same deformation with a different stress. And in a wave physics course, what we care about is the elastic behavior of media. That is to say, we are seismology. Well, we are thinking from the point of view of seismology. So we care about seismic waves. So we want to know what happens in the first seconds, minutes, maybe hours after a seismic event, after a rupture, after an earthquake. The media that we are dealing with are rocks within the earth, even very deep within the earth. So if we were considering not hours, but days, but months, weeks, years, millions of years, then we would observe a completely different behavior. It wouldn't make much sense to speak of elasticity, right? Because the media we are dealing with are viscous over long times. But in our approximation, for a short, if we only consider a short time after the event, we can approximate our media with perfectly elastic media. For a perfectly elastic media, the Hooke's law holds, which in one dimension, it says, it's a Hooke's law for the spring. It says, ut tensio sic vis. This is how Hooke formulated it in Latin a few centuries ago. The force is proportional to the deformation So in his mind, tensio was a deformation and this was the force. In the more modern form, we would write it like this. I'll explain you in a second what all this means. Or in component by component, it would read so if you have never been exposed to it, the vector notation can be a bit weird for you, okay? It's not a big deal, you know, you just stick to the component by component notation, and if you want to learn, just try, you know, to do the translation yourself. In component notation, I think it's pretty clear. We have, because we are not just considering the compression and expansion of a spring, but we are in 3D, in medium that can support, in media that can support shearing. We need a couple of parameters, okay, which we call lambda and mu, to describe how our medium responds to stress in various directions, okay? A response to deformation in various directions. So for a given deformation field, displacement field, for me, deformation and displacement are basically the same thing, okay? So for a given displacement field, U, the stress that's caused by this displacement is given by a first parameter that can be determined experimentally, lambda, times the divergence, okay, Einstein's notation. We are summing over the repeated index k. So divergence of the displacement multiplied by this symbol delta ij, which is called Kroneker's symbol. And it means basically that delta ij is equal to 1 if I equals j and is equal to 0 otherwise. Okay, so plus another parameter, which I denote with the letter mu, multiplied by, this is a bit funny, but you know, it's just the way it works. The derivative of the ith component of displacement with respect to the j's coordinate, plus, switch it around, derivative of the jth component of displacement times over the I Cartesian coordinate. Okay, so I bet that at least some of you have taken some geophysics course where people introduced the small deformation tensor and then, you know, if you introduce this tensor, the same thing reads, yeah, like tau j equals lambda plus 2 mu epsilon ij. some people like to write it that way. Why not? I mean, I don't like it because I don't see why we need to introduce one further entity, this deformation tensor, which doesn't really add anything to our understanding of the problems. But you find that in textbooks, and maybe it's helpful. It depends on how everybody's brain functions. So these three things, 1, 2, 3, it's the same thing, written in three different ways. So you maybe now, if you think about it, you see that if you define, notice very important, okay? This is actually, it's a good exercise in math to think carefully about the difference between this guy here, the divergence of u, see the little dot, okay? When you deal with vectors, little dots can be very, very important. Here, there's no dot between nabla and u, which means that this is not a divergence, but it's actually a tensor. So the divergence is a scalar, as you know. This guy is a tensor, so it's not ukxk, you multiply and sum up, but it's actually uixj. Okay, so if that would be the way to represent this expression in vector form. And then, of course, you see it becomes easy to understand that if you switch the indexes, you get the transpose, okay? So this little t here, it means transposition of this tensor, of this matrix here. Okay, but if you don't like the vector notation, it's totally fine. You can have a perfectly good, great career in acoustics and seismology, always using this index notation. It will just cost you some ink and some longer expressions when you write a paper. But it's perfectly fine. Okay, so the easiest way to think of this relationship is to think of it as an experimental, empirical law, okay? And indeed, over the 19th century, it was verified experimentally in many, many experiments. But the truth is that actually, well, let's see. Before I say what I want to say, yeah, let's finally get to Navier's law. So, okay, for now, this is an experimental law. Okay, so let's substitute inside our equation, and what we are gonna get is f I'm still gonna keep f just to write the most general form of this law. Which in vector notation reads and also doing a little bit of yeah, let's do it properly actually. So if you can do a little bit of algebra here. And in vector notation, you have f plus lambda plus mu gradient of the divergence. It gets difficult, I know. Mu plus mu, the Laplacian of u equals rho. Okay, so let's not worry about the algebra. You'll do these 3 steps, well, 4 as homework, right? You substitute this guy into here, do the algebra, you get this equation here, and then a little bit more algebra. So that would be 1, 2. You substitute 2 into 1, you should get 3. From 3, with a little bit of algebra, you get 4, and you can also get 4 bis if you translate 4 into vector notation. This is a nice homework. And we can talk about it if something is not clear next time. But before I leave you, I would like to emphasize a few things about the physics here. So first of all, what we have here is what we were looking for. I already told you that f, we have ways to deal with it. So everything else is a differential equation with only one unknown function, and that's the displacement. So it's difficult. It looks horrible, but you know, you can always feed it to a computer. Computers know how to solve numerically differential equations. Or you can find, if you, for simplified media, okay, if you have a media with very simple properties, like, for example, an infinite, unbounded, perfect elastic, isotropic, non-gravitating, elastic continuum, you can find also analytical solutions, and that's what we will try to do in the last lectures that I delivered to you. So that's the first thing, okay? This is something that we can solve. It's a differential equation that we can attack using math and informatics. The other thing that I want to tell you, okay, is that this is called, typically it's called Navier equation. Stokes, so the name Stokes, actually, I think probably that this guy would be called Navier-Stokes, I think. Because Stokes was, most of all, a fluid dynamicist who studied the cases where the medium is fluid or viscous rather than elastic. And that would result in a different relationship between tau and the displacement. If we have a fluid without viscosity, so that's basically what we did last week. It's water or air. This boils down to just no shearing, isotropic pressure, and we get back to the acoustic case. If you have viscoelastic media with shearing, then everything we did starting with Hooke's law doesn't hold anymore, but this equation still holds, okay? Because we haven't replaced tau in here. So we can go back to Navier-Stokes and use a different stress-strain, stress-deformation relationship in here. Okay, but in seismology, what we care about is Navier. There's one curiosity that it's more than just a curiosity that I want to tell you. I, and probably most of your teachers in the past and in the future, tell you that Hooke's law is an experimental law, okay? It's actually, it's true, but it's interesting to know that this equation was not derived in that way the first time around. When about 200 years ago, Navier, who was a French engineer, and other workers, the most important being Poisson and Cauchy, when these people derived this equation, they actually established the relationship between stress and strain mathematically, and they found that this relation actually follows from the simple assumption, if I'm not mistaken, that those intermolecular forces, okay, that works across the surfaces that I was telling you on Friday, they are basically, it's enough, I think, to assume that they die away very quickly as a function of the distance between those particles. So if you assume a force that pulls back towards one another two molecules, if you try to pull them apart, and pushes them apart if you try to push them, pulls them apart if you try to push them together, and it decays quickly with increasing distance, initial distance between the particles. Well, if you make that assumption, you're also going to get somehow, with a lot of math, the same relationship. And this was the work actually of Navier. The work of Navier, of Poisson, of Cauchy. There's an article. This is just a curiosity, right? For those of you that are really passionate about these things, Cauchy 1828, that basically works it out mathematically. So, yeah, just to point out that these are not trivial concepts. I mean, in a typical acoustics or geophysics, wave physics course, you are taught stress in 1 hour usually, but it took decades just to figure out this equation, and then other decades to prove it experimentally. It's a very important and very powerful result. Okay, do you have any questions? You have a lot. Yes, no, okay.
It's how many courses we have? How much many courses we have to? We have. I mean, how much courses we have to do? 2 or 1 or?
Oh, with me?
Yeah.
We are meeting on Wednesday, on Friday, and then we are done.
Okay.
So,
What about the exam? How we will pass it?
that's a good question. I was wondering, because it's the first time I teach at ICTP, so I need to speak with my colleagues, and I try to do exactly the same type of a test that they do. So when I find out, I'll tell you.
Okay.
Okay. I make for sure it will be something short, because I don't like exams. So I don't like to grade exams. I don't like to prepare exams. So, but yeah.
Okay.
But it depends on what ICTP rules are. evaluate you guys. So I find out, I'll ask my colleagues today.
Okay.
All right.
Thank you, sir.
Anything else? Okay, good. Let's try to play around a little bit with the vector notation, and I see you on Wednesday. All right. Thank you very much. Have a good day.
Thank you, sir.
Thank you, sir.
Guys, where BGC class?
Please, when are we
What?
having our
Where do we have the BGC class? Is it at the Stasi room or online? Has the man concluded on it?
maybe we ask
Uh,
on Slack?
the
Have they
professor did
muted
not.
us? Oh my